We are looking at the PiDP6 and Lisp, which was an early program for the PiDP6. I got into this when I read Stephen Levy's Hackers book. Gordon Bell, who was the architect of the PiDP6 and also other PDPs, said that the PiDP6 was really the star of the book or the protagonist. Of course, I wanted to relive that experience, that hacker story, and there's no PiDP6 around anymore. Only about 23 were built, and so I had to create my own in software.
So you're part of a group of people who do these reconstructions?
Right. So these are physical replicas of the panels. For the PiDP6, we don't have one yet, but it's planned because I don't think it's acceptable to not have a PiDP6 in the living room. So I started looking into the schematics and the description, which are online, and I thought, oh yeah, you can actually understand this, how this machine works. And I got started writing this emulator at a very low level. This is actually the second version of the emulator, but yeah, and it's running really nicely now. We have the graphical display of the peripherals, and so yeah, we're just gonna see this machine run. In the top left here, we have 4 units of deck tape or micro tape, as it was called originally, which is like a bit like a floppy disk, except earlier 1960s technology, magnetic tape. But you would take it with you, have your files on it, and so on. Down here we have a teletype, so you can type text to the computer and it can write something back. Here we see a display which can plot points and also has a character generator, so you can write text easily. Down here we have a paper tape reader and punch, but we're not actually going to use them here. And down here we have the front panel because we don't have a physical front panel yet. So we have to do with this for now. The PiDP6 was designed with a couple of goals in mind. One was to have a time-sharing system, a machine that can do scientific computation, like it has floating point instructions that the other machines don't have, the early ones, the smaller ones. And it was also designed to run Lisp more or less efficiently. That was one of the design goals. Lisp and the PiDP6 are actually siblings in this PiDP6 Lisp, this specific Lisp. They are kind of siblings because the MIT hackers were writing the Lisp, developing this Lisp on a blackboard, like on campus on MIT, and they would drive to DEC while they were building the first PiDP6 while the machine was not quite finished, and they would test their code there and debug it and so on. And so there's kind of a sibling relationship between the two. And I think it's good to actually be able to see it and use it. So we'll start by actually running Lisp, running some code, and then a little explanation of what makes the PiDP6 a good Lisp machine and how it differs a little bit from the IBM 704 that Lisp was originally developed on. So yeah, let's get started. We have a read-in key here, which you would normally push up, and I'm doing it here. And you could see the tape spin for a bit, and it has now loaded the deck type directory and is showing it on the display here. So let's first of all look at the code that I've written for this demo. Tico is the text editor which we'll use to investigate this. So we can use the light pen, which senses when a spot on the display has been intensified. So the computer knows where we are with the pen. So I'm using the mouse for this. So we pen Tico, and you can see Tico now being loaded from tape into memory. And we are now in Tico. You don't see it, but we are. And I have my Lisp program on tape unit 4. So I type 4, ER for reading from tape. Then the file name, it is ldemo1. Escape or alt mode, as it used to be called, delimits the name. And then Y for yanking one page from tape into the Tico buffer. 2 alt modes to actually do the thing, and you can see the tape spin. And here we have our code. Let's make that a little bit bigger. So this is PiDP6 Lisp. For people who are familiar with Lisp, this does look a bit antiquated, so there is no defun to define functions. You have to put expressions on the property list. And I just wrote two simple functions here, factorial to show recursion. Of course, nobody in their right mind would use recursion for factorial, but as a demo, it's okay. And a little greet function that just says hello. So we can move around in Tico here a little bit, but I don't want to go too much in depth into it. But the important thing is that Tico was meant to be a screen editor where you would see your text. Only later, when people used the machine at the same time with time sharing, that became a bit problematic because you only have one display, right? And so the screen support was ripped out for most versions of Tico. But the original is this. Okay, so that's our tape, our file on tape. We can go now. We want to load this tape, this file now from Lisp. So we have to exit Tico and go into Lisp instead. So with Control G and 2 Alt modes, I'm back in MacDump, and MacDump is for loading files from tape. I can also investigate, like get a directory listing on tape 4. So we see our file ldemo1 here, and this is the one I want to load. So back to tape 1, because that is where we have Lisp. Okay, so we pen Lisp, and it's loading it. So this version of Lisp is from around 1966. We found it like by luck on a deck tape image in binary form, and I restored the source code, and you can build it again from the assembly code, so on, because these things are not just around, that you cannot just download them somewhere and have all the PiDP6 software. This is archaeology you have to do. So we are in Lisp now, and we can do something simple like +3, 4, and it will print 7. So simple things. Now to read the file, there is a function called uread, and we give it a file name, which is ldemo1, and a tape unit, which is 4. So closing parenthesis, and the tape spins. Now to actually make Lisp read the file, we do Control Q, and we see it defines these two functions, factorial and greet. So let's try greet first. Oops, that was wrong. Parenthesis, greet, quote. Well, hello, Sean.
Hey.
And for factorial, you may be a bit surprised. If we calculate the factorial of 6, you will not recognize that as the factorial of 6, but that's just because it's an octal. We want to switch to base 10, perhaps. So there is a variable base that we can set to decimal 10, and now factorial prints the expected value. That's all for the demo of the machine. I now want to say a little bit about what makes the PiDP6 a good computer for Lisp. Okay, so a little bit about what makes Lisp tick and why the PiDP6 was made for Lisp. It was originally developed for the IBM 704, and that is important because there are two functions in Lisp, car and cdr, which people have talked about and complained that there are these cryptic names, and just a little bit about why these names are the way they are. An instruction word on the IBM 704 is split into, or it can be split into 4 fields. This is the prefix field, and it's 3 bits. This is the decrement field, and it's 15 bits. This is the tag field, which encodes an index register in the instruction. It's also 3 bits, and we have another 15 bits as the address field. So most instructions on the IBM 704 have the index field and the address field, like many other instruction sets as well. You have an address, a direct address, or you can modify it with an index register. This is very standard stuff. And in the upper part, you would encode the instruction opcode. Some instructions also have a decrement field, which is also address size. So we have 2 addresses potentially per instruction word, but most actually don't use it. But there are instructions in the IBM 704 to deal with these 4 fields. And that is kind of what led to these names, car and cdr. So car, people think that car and cdr were instructions on the 704. That is not true. These were just Lisp names. They were only named after the D and A here, and the It means content of the address field of a register and content of the decrement field of a register. And register really just means word. It's not a register as in flip-flops as we understand today. It's just a word of memory. So there are Lisp functions that get this part and get this part. And this is how we do Lisp structure in Lisp. You would put one part in the address part and another part in the decrement part. And then you have these cons cells that people sometimes draw where you have a linked list, and here you point to your data like A, B, and whatever, and eventually you would have a terminating value, nil, to indicate the end of a list. So this is how you build list structure, and you can, make more lists like here, can point that somewhere, and so on. So that is the story of car encoder on the IBM machine. And on the PiDP6, it's actually very similar. It's also a 36-bit machine like the IBM 704. But here we just split the word into two halves, just the left and the right half. And the car is stored in the left half, and the coder is stored in the right half. And these are 18 bits each, which is the address size of the PiDP6 and the PiDP10 later. And there are instructions for dealing with these half words, as they're called. In Lisp, you have these functions where you combine these cars and coders into chains of up to 4 levels of stepping through a list. The PiDP6 code that implements these car and coder operations, I have put here on the screen now. And to me, this is poetry. It's very short, sweet, succinct code. And this really highlights how you can implement these Lisp functions very neatly on the PiDP6, because it can deal with the left and right half of a word very nicely. So let's just see them in action. We already have 2 functions defined, so let's just look at their code, and we can use the get function. You can see that the expression property of the fact symbol just has this function, this lambda expression, which gets interpreted when we apply a fact to some number. So let's say we want to extract something out of this. First of all, let's make this a bit shorter. Let's define this as a variable. So coder takes the tail of a list, so it skips everything but the first element. And then car, the A happens afterwards, takes the first element of that. So cadder is the second element in a list. Lambda is the first. The list just containing n is the second element. We can take the third element like cadder, and if we want to take the first part of that again, maybe we can do cadder. It's very convenient to select parts of a list structure with all these with all the permutations of car encoders of length up to 4. And we see the code is just a page. Compare against the end of the string marker, and until that is the case, we just print the character on screen. So to see that in action, let's call the B command and give it hello. This is just a shell script, actually.